So everyone go to Team World 4 and we'll meet you there. So Team 4. Okay, so here we are. I think everyone's here. I'll wait one more second just to make sure no one's lagging behind. Okay, so I think we have everyone. So welcome to our world. um, we can pretty much just get started here. I think everything should pretty much be loaded. So if everyone looks at the black and red sign in the middle that says click here to begin the tour, that'll take us over to our knowledge space, and our team will introduce themselves. So everyone can click on the black sign. Okay, so assuming everyone's here, we can introduce some stuff. Starting with Dan.
Yeah, hi everybody. My name is Dan, and I'm a sophomore attending Bridgewater High School in New Jersey.
My name is Tony. I'm also a sophomore attending the same high school as Dan in New Jersey, and teammate for Team 4. Last name Zach.
Hi everyone. My name is Zach. I'm the team lead for Team 4. I'm a junior at Iowa State University studying aerospace engineering. With all the introductions out of the way, I'll hand it off to Tony, and he'll get you started on the tour. Thanks.
Okay, so if everyone will follow me, if we go straight ahead over here, we're going to start off with the objective that we were asked to do for this project, and what that was to create an alternative application or a tech transfer for one of the spin-off technologies that came from the James Webb Space Telescope. And the spin-off that we chose to find a tech transfer for was the iDesign Advanced Wavescan Studio, and that used the complete ophthalmic analysis system that was inspired by the JWST, and used in its creation. So if everyone wants to turn left, I'm going to talk to everyone about the first step in the engineering design process, which is identifying a problem in the world that needed to be solved. So as we thought about all of the different technologies that were used in the James Webb Space Telescope creation, it was obvious that something they all had in common was they could all be spun off for things that were useful in extremely precise situations that required extreme precision and accuracy. So we figured that one situation that needed precision and accuracy every single time was surgery, specifically for bone fractures. And one type of bone fracture that always needs a lot of precision and almost always requires surgery is called a comminuted fracture, which is basically the fancy way of saying when a bone shatters into multiple pieces. So currently, what doctors will do to figure out what the best form of surgery is, whether it's just trying to put the bones back in place and having them melt together, or if sometimes they use glue and sometimes they use screws. But what happens with this process is after the surgery is over, there's always a lot of uncertainty as to whether the surgery was a complete success. And what happens is the patients have to go to additional appointments for months, whether it's physical therapy or just going back to the doctor's office and getting x-rays, because there's always this fear that the bone will fail to grow back together and the patient could re-injure it. So that is pretty much the problem that we were trying to solve. And now I'm going to hand it off to Dan, who's going to talk to everyone about the criteria and constraints that we created for ourselves in the engineering design process.
Okay, so as Tony mentioned, I'll talk to you about about the criteria and constraints that we place on ourselves while working on the project. We put these guidelines in place so that our system could be as efficient as possible. The first guideline that we set for ourselves was that the machine had to be maneuverable enough for a surgical room. This was because doctors needed to be able to move the system wherever they felt necessary so that they could operate on their patient. The next guideline that we set for ourselves was that the machine needed to have the ability to scan bones from different angles. The reason for this was that because doctors needed to, the doctors wouldn't always be able to get to the position that they wanted to scan the bone, so they would have to be able to be aimed at many different angles. Our next conclusion was that the machine had to be able to sit perfectly still while scanning, so that the doctors could get a clear image to base their surgery on. Our final restraint was that the system had to work quickly enough so that the doctors and their patients were not in surgery for days at a time, but instead only for a few hours. All these limitations would make our system very efficient and possibly better than X-rays currently are. So now we will go back to Tony, who will talk to you about some solutions that we brainstormed during this project.
Okay, so it's Tony again, and I'm going to talk to you guys about the next step in the engineering design process, which was to brainstorm some different designs that could be used to solve this problem within the criteria and constraints that we set for ourselves. So we created two main design possibilities, and the first of these was a maneuverable arm type design, in which a arm kind of thing would be attached to a table with wheels at the bottom and a capsule at the end which had the scanner within it. And how it would work would be the base of the arm would be attached to the table with a swivel on it, and the arm would have one joint. And so a doctor could roll around the table and maneuver the arm in all different types of positions and until the scanner hovered over the patient's wound, and the doctor would cut open the patient at the point of the comminuted fracture, and then the scanner would be hovering over it and face downwards and perform the scan. And then while the scan was being performed, there would be a lever on the machine that would lock all the moving parts of the machine to ensure maximum steadiness for the scan. And then once the scan was performed, the image that it created would be sent to a monitor that could be studied very precisely by doctors prior to surgery. And the second design possibility that we brainstormed was an MRI-type capsule design, in which a patient would be cut open at the point of injury and then slid in this MRI-type capsule. And there would be a sliding scanner along the top of the MRI-type capsule, and the scanner would slide until it was hovering over the area of injury, and then, of course, be facing down and scan over the patient's fracture and then send that data to a monitor where it can be analyzed. So I'm going to continue talking about the next step in the design process, which is to actually select a design. And the design that we selected was the first one I talked to you about, which was the maneuverable arm. And the name for this was, the name we gave this was the fracture measuring wave scan system. So if you look on the right wall here, there's a couple of sketches of our design. So if you're looking at the first one that's closest to us, you kind of see the whole idea of the design with the box and the four wheels on the bottom, and then the arm with the joint and the scanner at the end. And then also there's a lock at the bottom that would lock all the moving parts. And then if we go over to the second picture, in the middle, it just shows the end of the arm, which would be the scanner, and would face down towards wherever the bone fracture was, and then create the very precise image and send it over to a separate monitor. And then if you look at the last sketch, this simply shows the lever at the bottom of the box, which would lock all the joints, wheels, and swivels, and this would stop any movement that was happening during the scanning of the patient. So just to go over a couple of strengths and weaknesses of this design, and this is a benefit because the doctor knows exactly where the scanner needs to go to get the scan that he needs. So it's useful that he has complete control over it. And now I'm going to hand it off back to Dan, who's going to talk about the merit of our design and some business applications.
I am now we'll talk to you about our content application and the merit of our design. The design that we came up with was feasible because it's made up of many different parts that have been tested already and proven to work. The design is also very simplistic, so that it can be applied commercially and can easily be placed in hospitals all over the world. So, the current wave scan technology can capture and create an image of up to 1,250 data points after scanning a 7mm pupil of an eye. This means that converting this wave scan technology will allow doctors to observe extremely precise grafts of bone, and this will allow for precise and more successful surgeries. The system is much faster and more accurate than X-rays, but there are still promise for advances in the future. An example of this is that a computer image taken from the scan could automatically tell doctors how to put a bone together in the correct positions. So now, if everyone would follow me over to the click here to teleport to the model area, we'll click on that, and Tony will talk to you a little bit about our models.
Actually, Zach had some technical difficulties. This was originally his section, but I think he's just getting back on now, and I think the program crashed. So instead, I'm going to talk to you guys about our modeling. And to create the models, we use SolidWorks and Pro 8. And Zach used SolidWorks because it was provided by a school, and he'd used it before. And me and Dan had never 3D modeled, so we used Pro 8 to free download off the internet. So here's our first model, which was the James Webb Space Telescope. And we used a computer 3D image that was interactive to try and we basically kind of used rulers against our computer screen to try and find out some of the dimensions of the James Webb Space Telescope, and then we made those into individual parts, and I sent them over to Zach, and he assembled this one. So as you can see, there's the mirrors on the front, the focal point, and yeah, so this is pretty much the James Webb Space Telescope design. You guys can click on that to examine it if you want for a little bit. I'll give you a minute to do that. So, next up, is everyone done looking at it? So, next, if we go up this flight of stairs, there's the second model that we were asked to create, which was the James Webb Space Telescope original spin-off, which is the iDesign Advanced Wave Scan Studio. And if you want to look at a picture of it, there's one over there on the wall. Basically what the iDesign Studio does is it's used for patients before LASIK surgery. They will put their eye up against it, and it will take a scan of their eye to get the contour of it.